In this video, I will give you an introduction to the method of images by working on a relatively simple example. I will start with reminding you what the first uniqueness theorem says, and this theorem is very important for the method of images. The first uniqueness theorem says that if you find a solution to Laplace's equation, this is Laplace's equation, that satisfies the boundary conditions, meaning if you find a function for potential that satisfies the boundary conditions of your problem, then you found the physically meaningful solution to the problem. You found it. Once you find it that satisfies the conditions, the boundary conditions, you're done. And this is an important, I've mentioned it before, this is a very important theorem. No matter what approach you take, once you find the solution that satisfies the boundary conditions, you have confidence that you found the solution. So here in this example, I will show you a different approach of finding the solution. In this example, I have a charge Q at position 0, 0D. This is the y-axis, this is the z-axis, and I know that that the x-axis goes out of the board towards you, out of the page. Now on the z equals 0 plane, I have an infinite grounded conducting plane. Okay, infinite, it extends everywhere on the xy plane. It is grounded, meaning the potential here is 0, and it is also conducting plane. That means that I have charges, mobile charges, probably mobile electrons, free to move anywhere on the plane. Now, what I want to do is to find the potential. Okay, this is my goal. What is the potential? And it will have to be as a function of the position vector. What is the potential for the area where z is greater than 0? I know when z is 0, I know that the potential is 0, and I know this because it's a grounded plane. And I'm interested in finding the solution in this part of the space where the charge Q is. Now, the boundary conditions, I already wrote 1. When z equals 0, the potential needs to be 0. But I also know what I have here is a charge very highly localized, and I have a conducting plane. I do anticipate, knowing how charges behave and how conductors behave, I do anticipate that there will be charges here with an opposite sign of the charge Q. This is grounded and conducting, so I do anticipate that there will be some polarization going on, and at the end, when I reach equilibrium, I will have some opposite sign charges near charge Q. Now I do know that if I am infinitely far away from where all the action takes place, I do expect that my potential will drop to 0. So as I go infinitely far away from the charge Q, I should expect that the potential goes to 0. So V needs to approach 0 when, so this is the, let's say, when the magnitude of the position vector is much greater than D. This is my second boundary condition. Now, I have set my two boundary conditions, and I will do the following, and then I will see if it works or not. Now, I do know that it works. So I'm going to look into what the potential is when I have the following scenario. the same coordinate system exactly as before, the charge q in the same location, and the charge minus q at the location of 0, 0 minus t. I'm gonna find, it's just 2 point charges, and I know what the potential is from a point charge. I will find the potential in this space, and then I will see if that satisfies the two boundary conditions. If it does, great, I found the solution to this problem. Now, the potential from a single point charge is 1 over 4 pi epsilon naught q over r. And I will remind you that r is the relative position vector that has the tip at the observation location and the tail at the source location. Now I have two source charges, two charges that contribute to the potential. So I'm going to start with one. The position of charge q is 0, 0, d. The position of the observation location where I want to find the potential is x, y, z. Using these two, the relative, let's call this observation. The relative position vector is r obs minus the r source, which is rq, and this will be x, comma y, comma z minus d. And if I find the magnitude of this r, then the magnitude of this will be the square root of x squared plus y squared plus z minus d squared. Let's separate the different sections, my work. If when I find the position vector of the charge minus q, this will be 0, 0 minus d, and I will skip a few steps, and I'm gonna go directly to the magnitude of that relative position vector, and this will be the square root of x squared plus y squared plus z plus d squared. I have the two magnitudes of the two position vectors, relative position vectors. Now this is equation, let's call this equation 3 and equation 4, and this one is equation 5. I will write the potential due to the charge q will be 1 over 4 pi epsilon naught q divided by the magnitude of r, and this is given by equation 4, so it will be the square root x squared plus y squared plus z minus d squared. Now let me use this notation: the potential that charge q creates at the observation location, and the potential that charge minus q creates at the observation location is going to be 1 over 4 pi epsilon naught minus q, the square root of x squared plus y squared plus z plus d, and that term squared. Now the potential at the observation location from both of them is the sum of the two, and this will be, let's take q out as a common factor, and then I will have 1 divided by the square root of x squared plus y squared plus z minus d squared plus the minus 1, the square root of x squared plus y squared plus z plus d squared, and then we close the bracket. This is the potential at the observation location. Now, I want to remind you, this is the potential for this system, okay, where I have the charge plus q and minus q. Now, as I said, I know what the potential is from 2 point charges, and I found it. Now, what I will do, I will test to see if this solution satisfies any, if any, of the 2 boundary conditions. When I plug in z equals 0 here and here, I get exactly the same term, with the difference that there is a minus sign. So from equation 6, when I plug in z equals 0, I get that the potential at the observation location is exactly 0, because the 2 terms cancel out. Again, from equation 6, when I have that x squared plus y squared plus z squared is much greater than d squared, then this term becomes very large, and that denominator also becomes very large, which makes my potential to approach 0 as I move infinitely far away from the charge q. So this equation 6 satisfies both boundary conditions for my original problem, for this one. This means that I just found what the potential is in the space where z is greater than 0. This is the solution to my original problem. Now, the reason why it is called the method of images is because I started with the charge q at location 00d, and the solution to my original problem was found by placing the charge minus q at the mirror location of charge q, 00 minus t. It has the opposite charge, and it is at the mirror image location of charge q. By solving that problem, I was able to find the solution to the original one. So this is why this is called the method of images, and it is very useful so long as you can find the solution that satisfies the boundary conditions. But it is very useful because we have the first uniqueness theorem. Okay, don't forget that.